Okay, back to chapter 3 and back to the physics finally now. We've been talking about reminding ourselves about some facts about right triangles, which then were relevant to the definitions of components of scalars and vectors. We drew vectors as arrows and represented them by components. And we also talked about how to add and subtract and scalar multiply vectors. Now we're finally going to use what we've learned in the first part to be able to generalize the chapter 2 ideas, the idea of velocity and acceleration in 2 dimensions and 3 dimensions. What I'm showing here is a picture of an ant following a path in the xy plane. Now it kind of looks like an x versus t graph, but t isn't anywhere here. This is the x-axis, this is the y-axis. This is supposed to be, like the plane of the chalkboard or something like that. And what I'm drawing here is the path an ant took through the plane as time went on. The ant was here at time t1, was here at time t2, and we're going to want to talk about, for one of our first definitions, the displacement vector. What was its displacement between time t1 and t2? What we just do is draw a vector that from where it was at t1 to where it was at t2. That's the displacement, and we'll denote that by delta r. It's called delta. Delta always represents a subtraction. It means r final minus r initial. So if you really wanted to draw it as a subtraction, we could say r1 is where it was at time t1 relative to the origin. r2 is a vector that shows where it was relative to the origin at time t2. And the subtraction, of course, when the tails are co-located like that, goes from tip to tip in the usual from initial to final kind of way. But we're not going to suppress that kind of picture here. And essentially use the same definition that we used in 1 dimension for the average velocity vector. We're going to denote the average velocity vector here by a v for velocity with a vector symbol over the top of it, and then a little bar over that. That bar always represents averaging. So we're going to get an average velocity vector between time t1 and t2. And the definition we used back in chapter 1 was just displacement over time. We're going to do the same thing here, except our displacement now is legitimately a vector. It could be a vector back in 1D, but the vector was sort of boring that it just pointed along the x-axis. So that's delta r over delta t. The average velocity is how far and in which direction it went divided by how much time it took, or r2 minus r1 over delta t, if you picture the r1 and r2 that I showed you a moment ago. We are not concerned with, nobody really cares about the average velocity vector very often. What we're concerned with and what we want to know is, what is the velocity right at this time t1? I don't want to know an average between 2 times. I want to know exactly how fast and in which direction was it moving at t1. And the way we're going to construct that is, same definition we gave before. Take the average velocity, but take it over smaller and smaller time intervals. In other words, go from t1 to t2 here, and then let t2 get smaller so it gets a little bit closer. t2 even smaller, so delta t is getting smaller and smaller. So move t2 closer, move t2 closer still, and we've got to do the limit of that process as delta t goes to 0. Now you might be getting worried that this vector looks like it's going to get smaller and smaller and shrink to nothing, because as t2 goes to t1, these two dots will get close to each other. But that's not a problem for this. Yes, delta r is getting smaller and smaller, but the denominator delta t is also getting smaller and smaller. Or another way to think about it is, we're taking that vector delta r and we're scalar multiplying by 1 over delta t. And as delta t gets small, 1 over delta t gets huge. So we take this small vector and we scalar multiply by a huge number, and it tends to stay roughly the same length as you let that delta t get close to 0. Okay? And I hope it's pretty easy to see that as you let it get close to 0, it's going to get closer and closer to a vector that is tangent to the path that the ant is on. In other words, as these 2 points get closer and closer together, delta r is approximately tangent to the path, and v is just a vector that's a rescaled version of that. So v is going to be tangent to the path as we let that delta t goes to 0. Okay, so if you draw the path of something, either in 2 dimensions, or even as, a fly flying through 3-dimensional space and we visualize its path, the velocity vector is always parallel to the object's path. So here it is at time t1, maybe at time t, if t1 is over at some earlier time, this vector is parallel or tangent to the path right there. Here it is at some other time. It should be tangent to the path, right? If I draw a tangent line, it should be like a ray that's half of that tangent line. Now, the meaning of speed is the same thing. It's how, when we talk about speed, that means how fast are you going? And that is represented by the length of this vector. And to calculate the length of the vector, if we know the components of the vector, if I know the y and x components of the vector, I can use the Pythagorean theorem to get the speed, which is just the square root of vx squared plus vy squared. Vx and vy might have minus signs in them, but when we square them, the minus signs go away, so it doesn't really affect anything. So speed is a scalar. Speed doesn't have a direction. When I say I'm moving at 5 miles an hour, I'm not giving you any information about the direction I'm going. I'm just telling you how fast I'm going. Okay, that's velocity. And now, while we're in the groove, we're going to just take these same slides and do the same definition for acceleration. Okay? Just the same definitions we gave back in chapter 2. We're going to use the same things now, except that change in velocity is going to be a vector. So, we'll first calculate the average acceleration vector between time t1 and t2. So I'm imagining it has a velocity vector v1 at time t1 and v2 at time t2. We have to so it's just going to be delta v over delta t. That's exactly what we did back in chapter 2 for one-dimensional motion, but now that delta v is a difference in 2 vectors. It's going to be v2 minus v1 is delta t, the change in the velocity vector. Okay, how do I visualize that vector delta v? Well, I can redraw v1 and v2 with their tails at the same location. So notice I've moved them over here without changing their orientation. It's just that I've put their tails at the same location. And to get delta v, I draw from the initial tip to the final tip. So this is a picture of delta v, or v2 minus v1. So what this is saying is that the average acceleration vector is a scalar multiple, 1 over delta t times v2 minus v1. So in between these 2 times, the average acceleration was kind of pointing in that direction. It's a rescaled version of this blue vector over here. Again, nobody cares about, or very few people care about, the average acceleration vectors between 2 times. We're using it as a stepping stone to get to the notion of what is the acceleration of this ant right at this time? How fast and in which direction is it accelerating? So the definition of the acceleration vector, which is defined only at a single time, is take the average acceleration vector over a time interval and let that time interval get smaller and smaller and smaller so that you always include the time that you're interested in. So I'm going to let this t2 get closer and closer and closer to t1, and then I'm going to imagine calculating delta v, and then the acceleration vector will be a scalar multiple, a rescaled version of that vector. Okay? The acceleration magnitude, there's not really a good name for the length of the acceleration vector, but we usually call it the acceleration magnitude. Again, is if I know that vector's x and y components, then I use the Pythagorean theorem to calculate the acceleration magnitude. All right, let's do a worksheet problem, continuing on the same worksheet that you've already been working on. We've got a radio-controlled car moving in the xy plane. Imagine we know what the xy axes are. It's driving around on the floor. And at time t1, its velocity is represented by this vector. At time t2, it's turned a little bit, and it's going with what looks like the same speed, but in a different direction, more down and to the right. Or, we're supposed to be looking down at the floor, I guess, here. What I want you to do is draw and label a picture of the change in velocity vectors between those 2 times. Okay, and so the average acceleration would be along the same direction. It would be a rescaled version of it. Same thing here, except this, The reason I'm doing this is because this is going to be a case that comes up a little bit later on, so there's a point I want to make. So at time t1, the car was going at a certain speed in this direction. At time t2, maybe after it's gone on a long path around, at time t2 it happens to be moving with the same speed in the opposite direction. Draw what delta v looks like. And we'll be back with the solution to that, so try it yourself.